Welcome back, everyone, to the Deep Dive. Ready to explore some more cutting-edge tech?
Absolutely. Always excited to jump into the latest advancements.
Well, today we're diving headfirst into the world of AI. Specifically, how on earth we build systems powerful enough to run these crazy complex models everyone's talking about.
Right, because it's one thing to have a brilliant AI algorithm, but without the hardware muscle to actually execute it.
It's basically useless, right?
Pretty much. So we're focusing on what's called AI inference processing. That's the stage where an AI model actually generates its output, gives you those smart results.
Makes sense. So it's not about training the model, it's about putting it to work.
Exactly. And our deep dive today is all about how different computer architectures handle that process, especially with the just massive amounts of data involved.
So kind of a hardware showdown.
You could say that.
Yeah.
And there's this really interesting question we're going to try to answer. Can a technology we all use every day, fiber optics, actually be a game changer in this AI hardware race?
Ooh, now that's intriguing. Fiber optics, like for internet. Inside AI chips.
You got it. And more specifically, can fiber optics help those smaller, more conventional AI chip designs go head-to-head with the giants out there, the so-called wafer scale chips?
Okay, I'm hooked. Lay it on me. What are these contenders we're talking about?
On one side, we've got Nvidia's Blackwell architecture. This is like the epitome of a super high-performance, small format chip, really pushing the limits of speed and efficiency.
Small format meaning it's still a single chip, not one of those giant wafer things.
Right, but don't let that fool you. It's packing some serious heat. They're achieving insane throughput and crazy low latency. We'll dig into how they pull that off, all the clever design and super fast connections involved.
Sounds impressive. And who's the David to their Goliath?
That would be Cerebras and their wafer scale engine, or WSE for short. This is the radical large format champ. Literally an entire silicon wafer transformed into a single mega processor.
Whoa, so not combining multiple chips, but one chip that is the wafer.
Exactly. The whole focus here is massive parallelism. Hundreds of thousands of processing cores all working together at once, plus a ton of memory right there on the wafer. A whole different beast.
Okay, so two totally different approaches, both aiming for AI domination. But why does this even matter to us non-engineers?
Well, think of it this way. You could have the world's fastest car, but if it's stuck in traffic...
It's going nowhere fast.
Precisely. And it's the same with AI. You can have insanely powerful processing cores, but if the data they need can't move around quickly enough...
The whole system slows down.
Yep. And those data pathways, called interconnects, are absolutely vital. And they can easily become bottlenecks that cripple performance, no matter how good your processors are.
So this all comes down to efficient data flow.
Yeah.
Got to keep things moving.
Exactly. And that's where our central question for this deep dive comes in. Can fiber optics be the key? Can using light to move data within these chips unlock a whole new level of performance, maybe even level the playing field between these different architectures?
Okay, I'm ready to get into the nitty-gritty. Let's start with Nvidia's Blackwell. What makes this chip so special?
Well, first off, it's purpose-built for this new era of generative AI. The stuff that's making headlines, creating images and text and all that.
Right, like those chatbots everyone's either loving or fearing.
Exactly. And it's NVIDIA's biggest GPU ever. We're talking a mind-blowing 208 billion transistors crammed onto a single chip.
208 billion. My brain can't even comprehend that many of anything.
It's a lot. And it's that density that gives them so much computational power. To pull that off, they're using a really cutting-edge manufacturing process from TSMC called 4NP. It allows for packing all those transistors in without the chip becoming, the size of a dinner plate.
So more transistors equals more power, essentially.
Yeah. And the performance numbers are crazy, up to 20 petaflop PS and FP4 precision.
Petaflop PS, right. Remind me what that actually means.
Basically, it's a measure of how many calculations the chip can do per second. And petaflop PS means quadrillions of calculations. It's a measure of raw processing power, especially for the kinds of math AI loves.
So, mind-bogglingly fast. But you said Blackwell is a multi-die approach. Does that mean it's not truly a single chip?
It's a clever trick. Essentially, it's two very large silicon dies, but they're connected by this ultra-fast interface called NVHBI. It has a bandwidth of 10 terabytes per second.
Terabytes per second. That's like transferring a whole high-definition movie every fraction of a second.
Yeah, pretty much. And that insane connection speed makes those two dies function as a single unified processor. You don't even notice it's two separate pieces.
So it's like having two super-fast brains working perfectly in sync.
A great analogy. And it's not just theoretical speeds either. They've been putting Blackwell through its paces with these standardized AI benchmarks called MLPerf inference.
Right, those are kind of like the Olympics for AI hardware.
Exactly. And the results are pretty impressive. Their big system, the Nvidia GB200 NVL72, which uses 72 of these Blackwell GPUs all linked together, set new records on the Llama 3.1405B benchmark.
Okay, break that down for me. What's Llama and why is that benchmark important?
So Llama is a large language model, meaning it's one of those AI systems that can generate text, translate languages, write different kinds of creative content, all sorts of stuff. And this particular one, the 3.1405B version, is huge. 405 billion parameters, which basically means it has a ton of internal knowledge.
So the bigger the model, the smarter it is generally.
You could say that, yeah. More parameters mean it can understand and generate more complex and nuanced language, but those huge models also require a ton of processing power to run, which is where Blackwell shines.
I see. So it aced the test of handling this massive language model.
It did. And the key thing to note is the scale of improvement. They're seeing up to 30 times higher throughput than their previous generation of GPUs. That's a massive leap forward.
That's huge. And it's not just for these giant data center systems either, right?
Nope. They've also shown really impressive performance gains on smaller setups. Their DGX B200 system, which has just 8 Blackwell GPUs, showed big improvements on the Llama 270B interactive benchmark.
So even on a smaller scale, it's still super efficient.
It is, and that scalability is really important because not every application needs hundreds of GPUs.
Makes sense. So what's contributing to these performance gains? Is it just the raw power of those 208 billion transistors?
That's definitely a big part of it, but there are a couple of other key ingredients. One is their support for FP4 precision, which is powered by their second-generation transformer engine.
Okay, that's a mouthful. What does all that mean in plain English?
So transformer models are the underlying architecture for most of these modern large language models. And FP4 precision basically means they've found a way to represent the numbers used in the calculations with less precision.
Less precision? Doesn't that mean less accuracy?
You'd think so, but it turns out that for these AI models, you don't actually need all those extra bits of precision. By using FP4, they can do the calculations much faster without sacrificing much, if any, accuracy.
Ah, so it's like finding a shortcut that doesn't compromise the quality of the result.
Exactly. It's a clever optimization. And then, of course, there are those all-important interconnects we talked about. Nvidia has really stepped up their game with the 5th generation of their NVLink technology.
Remind me, NVLink is how the GPUs talk to each other, right?
You got it. And this new version is a beast. Each link can handle a whopping 50 gigabytes per second, and it can do that in both directions simultaneously.
Okay, so data is flying back and forth between those GPUs at insane speeds.
It is. And each Blackwell GPU has 18 of these NVLink connections, which totals a mind-boggling 1.8 terabytes per second of bandwidth per GPU.
So even though they're separate chips, they can act almost like a single unit, thanks to NVLink.
Precisely. But it doesn't stop there. They also have the NVLink switch, which takes this high-speed communication to the next level.
How so?
Well, within a single server, NVLink is great for connecting a handful of GPUs. But with the NVLink switch, you can connect multiple servers together and treat them as one giant computing resource.
So you could have like a whole rack of servers, all with their Blackwell GPUs, acting like one massive supercomputer.
Exactly. And it supports up to 130 terabytes per second of total bandwidth. It's what allows them to train and run those truly gargantuan AI models that would be impossible on a single server.
So they've really thought about how to scale this up.
They have. And then there's one more NVLink trick up their sleeve. NVLink-C2C.
Okay, another acronym. What's that one for?
So in their GB200 superchip, they combine the Blackwell GPUs with their Grace CPUs on the same package. And NVLink-C2C is specifically designed for high-speed communication between those two different types of processors.
So it's like a dedicated superhighway between the brains and the brawn of the system.
A perfect way to put it. The CPU can quickly feed the GPUs the data they need, and the GPUs can send back the results without any bottlenecks. It's all about optimizing that collaboration between different parts of the system.
It's amazing how they've thought of all these ways to eliminate bottlenecks and keep the data flowing.
It's all about efficiency and this scale. Before we move on, just to recap, here are the key specs for Blackwell. The B200 GPU, 208 billion transistors, TSMC 4NP process, around 18 petaflops peak FD4 performance, up to 192 gigabytes of HBM3 memory with up to 8 terabytes per second of bandwidth, and that 1.8 terabytes per second NVLink bandwidth per GPU. And when you scale up to their NVL72 system, you get that potential 130 terabytes per second NVLink switch bandwidth.
Wow, it's seriously impressive. But now let's switch gears completely and talk about Cerebras and their completely different approach with the wafer scale engine.
Right, this is where things get really interesting. Remember, while Nvidia is pushing the limits of what you can do with individual chips, Cerebras is taking a totally different route.
They're not just playing the same game, they're inventing a whole new game.
Exactly. They said, why try to connect a bunch of chips together when we can just turn the entire wafer into one giant processor? And that's their wafer scale engine.
So it's not just a bigger chip, it's a fundamentally different way of thinking about chip design.
It is, and their latest version, the WSE3, has specs that are almost hard to believe. It has 4 trillion transistors, that's trillion with a T, and an unbelievable 900,000 AI-optimized cores, all on a single wafer.
900,000 cores. It's like an army of tiny processors.
It is, and to keep all those cores fed with data, they've also integrated a whopping 44 gigabyte of SRAM memory directly onto the wafer.
SRAM, that's that super fast memory.
Right.
Yeah.
It's much faster than the DRAM you usually find in computers, but it's also more expensive and takes up more space. But because Cerebras is using the entire wafer, they have the space, and it lets those cores access data incredibly quickly.
So no waiting around for data to arrive from some distant part of the system.
Exactly. And then there's the memory bandwidth, which is just phenomenal, 21 petabytes per second.
Petabytes. I don't even know how to compare that to anything in the real world.
It's hard to wrap your head around, yeah. But basically, it means that those 900,000 cores have a constant and enormous supply of data readily available. It's another key advantage of that wafer scale design.
So they've basically eliminated the data bottleneck completely.
Well, within the wafer itself, pretty much. And a big part of how they achieve that is with their on-wafer interconnect.
Right, that network of connections between all those cores.
Exactly. And because everything is on the same piece of silicon, those connections can be incredibly fast and efficient. There's no need to go off chip, which introduces delays and complexities.
So it's like having a city where every building is connected by super fast, dedicated highways.
A great analogy. And it really shows in the performance they're getting. For example, they've reported over 2,200 tokens per second for the Llama 3.37 EB model, which is faster than what's typically seen on traditional GPU-based systems.
So it's living up to the hype.
It seems so. They've also claimed significant speedups compared to NVIDIA GPUs in those massive cloud environments. For the Llama 3.170B model, they've reported up to 20 times faster inference in some scenarios.
20 times faster. That's a bold claim.
It is. And they've also been breaking records with the even larger Llama 3.1405B model. They're getting almost 1,000 tokens per second with that one, and their time to first token is only 240 milliseconds.
Time to first token, what's that?
It's basically how long it takes for the model to start generating its output. It's a really important metric for interactive applications like those chatbots we talked about, because you don't want the user waiting forever for a response.
Makes sense. So it sounds like this on-wafer interconnect is the secret sauce for Cerebras.
It's definitely a major factor. On the WSE3, they've achieved an aggregate core-to-core bandwidth of 214 petabits per second. That's just an astronomical amount of data flowing between those cores.
So they're not just throwing a ton of cores at the problem. They're making sure they can all communicate effectively.
Exactly. It's a really clever approach. Just to summarize the key specs for the WSE3, 4 trillion transistors, TSMC 5mm process, 900,000 AI cores, 44 gigabytes of on-chip SRAM, 125 petaflops peak AI performance, that massive 21 petabytes per second memory bandwidth, and the 214 petabits per second interconnect bandwidth. It's truly a unique and incredibly powerful piece of hardware.
Absolutely. Okay, so we've got these two very different philosophies. Nvidia with their incredibly advanced individual chips connected by high-speed electrical interconnects, and Cerebras with their monolithic wafer approach focusing on massive on-chip parallelism and bandwidth. Now, let's step back a bit and talk about the bigger picture. What are the inherent limitations and bottlenecks in AI inference that both of these architectures are trying to overcome?
One of the biggest challenges, as we touched on earlier, is memory bandwidth. These large language models, well, they're huge. And for every word, or rather every token they generate, the system needs to access those massive model parameters and any intermediate data from memory.
So it's a constant back and forth between the processing units and the memory.
Exactly. And that can create a real bottleneck no matter how fast your processors are. If they're constantly waiting for data from memory, the whole system slows down.
And this is one area where the two architectures take very different approaches.
They do. With GPU-based systems like Blackwell, they typically rely on external high-bandwidth memory, or HBM for short.
So the memory is not on the same chip as the GPU.
Right. It's a separate chip, but it's still much faster than traditional DRAM. However, because it's external, there's still some latency and overhead involved in communicating with it.
So even though it's fast, it's still a potential bottleneck.
It can be, yeah. But with Cerebras' WSC, they've taken a different route. They've integrated that massive 44 gigabytes of SRAM directly onto the wafer right next to the processing cores.
So it's like having a giant, ultra-fast pantry right next to the kitchen where all the cooking happens.
The perfect analogy. It minimizes those delays and lets the cores access data incredibly quickly.
Smart. So memory bandwidth is one bottleneck. What else are these architectures grappling with?
Another big one is communication between processing units. In a multi-GPU system, the traditional way to connect those GPUs is with PCIe.
PCIe, that's the same interface used for graphics cards and other peripherals in regular computers, right?
It's the very same. And it works well enough for those applications. But when you're trying to connect multiple high-performance GPUs that need to exchange data constantly, PCIe starts to show its limitations.
Because it's not designed for that level of communication.
Exactly. It has relatively limited bandwidth and higher latency compared to more specialized interconnects.
And that's where NVIDIA's NVLink comes in, right?
Right again. NVLink is designed specifically for high-speed communication between GPUs. It offers much higher bandwidth and lower latency than PCIe, which is crucial for making those multi-GPU systems perform effectively.
So NVLink is like upgrading from a dirt road to a superhighway.
Exactly. And Cerebras, with their on-wafer approach, has kind of sidestepped this whole issue.
Because all their cores are already on the same chip.
Exactly. They don't need to worry about external connections between chips, because their on-wafer interconnect provides incredibly fast and efficient communication between all those cores.
Clever. So they've kind of solved that problem by design.
They have. But there's another fundamental limitation that both architectures have to contend with: the von Neumann bottleneck.
Okay. The von Neumann bottleneck, that sounds ominous. What is that?
It's a term that describes the classic architecture of computers, where you have the memory where data is stored separate from the CPU where the processing happens. And this separation means that the CPU is constantly having to fetch data from memory, which takes time and creates a bottleneck.
So it's like having a factory where the workers have to run back and forth to a warehouse every time they need a new part.
Exactly. It's inefficient. And with these AI models that require tons of data, that bottleneck becomes even more pronounced.
And how are these architectures addressing that?
Well, Cerebras, with their large on-chip memory, is trying to minimize the distance data has to travel. By having the memory right next to the cores, they reduce that fetching time significantly.
So it's like bringing the warehouse right into the factory.
Exactly. And Nvidia is also working on ways to mitigate the von Neumann bottleneck through clever caching and memory management techniques. But it's a fundamental challenge in computer architecture.
Okay, so we've identified some serious challenges in moving data efficiently for AI inference. Now let's talk about a potential solution. Fiber optics. We know it's great for high-speed internet, but how can it revolutionize the inner workings of these AI chips?
That's the really exciting part. Fiber optics offers several key advantages over those traditional copper interconnects. First and foremost, it's incredibly fast. Data travels at the speed of light through those optical fibers.
So significantly faster than electrical signals.
Oh, absolutely. And that translates into much higher bandwidth. You can move a lot more data through a fiber optic cable than you can through a copper wire of the same size.
And I imagine it's more reliable too, right?
You're absolutely right. Fiber optic signals don't degrade as much over distance, so you get a much cleaner signal with less interference. And because light travels so fast, you also get much lower latency.
Lower latency, that's crucial for these real-time AI applications, isn't it?
It is. And fiber optics is also immune to electromagnetic interference, which can be a big problem in those densely packed data centers.
Right, all those electrical signals can create a lot of noise.
They can. So using light instead of electricity has some big advantages. Now, you might be thinking, okay, fiber optics is great for long distances, but how does it help at the chip level, where everything is so tiny?
That's a good question. Doesn't light need space to travel?
It does, but even at those tiny scales, the latency advantages are significant. We're talking about potential latencies in the nanosecond range for communication between chips. And new optical I/O technologies are emerging that could even offer competitive latency for communication within a chip, rivaling those electrical interconnects.
Nanoseconds? That's incredibly fast. And what about bandwidth?
Well, we're already seeing fiber optic interconnects for chips that can handle over 100 gigabits per second per lane. And with techniques like wavelength division multiplexing, where you send multiple light signals at different wavelengths through the same fiber, we could potentially reach terabits per second.
Terabits per second, that's just mind-boggling.
It is. And the key technology that's enabling all this is silicon photonics.
Silicon photonics, that's about integrating optical components onto silicon chips.
Right, exactly. It lets us create those tiny lasers, modulators, and detectors needed for fiber optics, all on the same silicon wafers that we use for making chips. It's a game changer.
So it's like shrinking down the entire fiber optic infrastructure to the chip level.
Exactly. And then there's another trend that's really exciting, co-packaged optics.
Co-packaged optics, what's that?
It's all about bringing those optical components as close as possible to the processing chip, sometimes even within the same package.
And what's the benefit of that?
Well, it minimizes the distance that electrical signals have to travel, which reduces both power consumption and latency. Remember, every time an electrical signal has to travel a certain distance, it loses some energy and slows down a bit.
Right, so by converting those signals to light as early as possible, you avoid those losses.
Exactly. And we're already seeing companies like Nvidia implementing co-packaged optics in their high-performance networking switches. And Cerebras is working with a company called Renovis to explore wafer-scale co-packaged optics.
So both companies are betting on fiber optics for the future.
They are. It's really the only way to keep up with the ever-increasing bandwidth demands of AI. To really compare how different these technologies are, here's a quick rundown of electrical versus optical interconnects. For bandwidth, electrical is usually around 40 gigabits per second per lane at most, while optical can go way beyond that into the terabits per second. For latency, electrical increases with distance and frequency, while optical has very low propagation delay, although the transceivers can add some latency. Electrical really suffers over long distances, while optical can go much further with minimal signal loss. Electrical also uses more power the faster and further it goes, while optical can be more efficient, especially at high speeds and long distances. Then you have electromagnetic interference, which is a big problem for electrical but not for optical. Cost-wise, electrical is cheaper for short distances, but optical is catching up. And finally, optical tends to be more reliable and robust overall.
Okay, so fiber optics clearly has a lot going for it. But how does all this specifically apply to the AI inference architectures we've been discussing? Let's start with Nvidia's Blackwell. How does fiber optics fit into their strategy?
Well, for Blackwell, fiber optics is already essential for scaling beyond single servers. Their Blackwell Ultra platform is designed to work with superfast networking technologies like Nvidia Spectrum-X Ethernet and Quantum X800 InfiniBand.
And those often rely on fiber optics, right?
Exactly. They use fiber optic cables for the physical connections, which allows them to achieve that incredible 800 gigabits per second throughput per GPU.
So NVLink is great for connecting GPUs within a server, but fiber optics is what lets them connect across all data center.
Exactly. And NVIDIA's investments in co-packaged optics for their networking switches clearly show that they're serious about using fiber optics to boost AI performance at scale.
Makes sense. So what about Cerebras? How does fiber optics come into play with their wafer scale approach?
Well, Cerebras is also exploring the potential of fiber optics, mainly to enhance their off-wafer communication. Remember, their on-wafer interconnect is fantastic for connecting all those cores on the wafer itself.
But they still need to connect to external memory and other systems.
Right, and that's where fiber optics can come in. Their partnership with Renovis is all about exploring wafer-scale co-packaged optics.
So integrating those optical components directly onto the wafer.
Exactly. It would let them achieve incredibly high bandwidth off-wafer communication, boosting overall performance.
Okay, so both companies are embracing fiber optics in different ways. But the big question is, can these advancements in fiber optics actually help smaller format chips like Blackwell compete with the massive on-chip capabilities of Cerebras' WSE?
That's the million-dollar question, or maybe the billion-dollar question in this case. And the potential is certainly there. If those multi-chip systems can leverage high-bandwidth optical interconnects to communicate almost as fast as Cerebras' on-wafer interconnect, it could really shake things up.
And the progress in optical I/O and silicon photonics is definitely promising.
It is. And standardization efforts, like UCIe, now including specifications for optical interconnects, are also helping to pave the way. This will make it easier for different companies to build interoperable optical components.
So it's not just about the technology itself, it's about creating a whole ecosystem.
Exactly. And when you consider that multi-chip systems can easily scale up to dozens or even hundreds of GPUs, connecting them all with high bandwidth fiber optics could create some truly massive and powerful AI systems.
So it sounds like fiber optics could really help those smaller chip designs close the gap with the wafer scale approach.
They could. It's a really exciting development. What do you think the future holds for these different architectures?
Well, it's clear that the way we move data within AI systems is becoming just as important as the processing power itself.
Absolutely. And the experts seem to agree that optical interconnects are the future. They're the key to keeping up with the ever-growing demands of AI.
We're already seeing fiber optics everywhere in high-performance computing, and co-packaged optics is definitely on the rise.
It is, and everyone is focused on optimizing AI infrastructure, making it faster and more cost-effective.
It's all about finding that sweet spot between performance and efficiency.
Exactly. And the experts have some interesting opinions when you compare Nvidia and Cerebras head-to-head.
What do they say?
Well, the general consensus is that Cerebras has a clear advantage in raw inference speed and memory bandwidth, especially for those giant language models. But Nvidia still has a lot going for it with its mature CUDA ecosystem and its broader applicability across different AI workloads.
So Cerebras is the specialist, and Nvidia is the generalist.
You could say that, yeah. But some experts believe that Cerebras's wafer scale approach could start to challenge NVIDIA's dominance in the long run.
It's a fascinating battle to watch. So just to recap, we've got NVIDIA with their multi-chip strategy, focusing on advanced electrical interconnects and scalability, and Cerebras with their revolutionary wafer scale approach, maximizing on-chip communication and memory bandwidth. And fiber optics could be the key to bridging the gap between these two philosophies.
It's true. We have NVIDIA balancing performance, scalability, and manufacturability with their multi-chip approach. And Cerebras going all in on chip integration and raw speed for those massive language models. It'll be interesting to see how fiber optics further evolves these approaches.
Right. If optical interconnects can catch up to the speed of Cerebras on-wafer interconnect, it could really level the playing field.
It could. And then the choice might come down to other factors, like cost-effectiveness, flexibility, and the specific requirements of the AI workload.
Right, because different applications have different needs. Some might prioritize low latency, while others might need massive throughput.
Exactly, and the manufacturing costs and complexities of these different approaches also come into play. Ultimately, the best solution will depend on the specific use case.
So where do you think the future of AI inference interconnects is headed?
Well, I think it's safe to say that things are going to get a lot more optical. We'll probably see co-packaged optics becoming the norm, as it offers the best combination of performance and efficiency. And continued innovation in silicon photonics will be crucial for making those optical interconnects even faster and more compact.
So light is going to play a bigger and bigger role in the future of AI.
Absolutely. And who knows what incredible new AI applications will become possible as we overcome those data transfer limitations.
It's an exciting time to be following this technology. So for our listeners out there who are curious to learn more, what are some areas they could explore?
Well, I'd encourage them to dive deeper into silicon photonics, co-packaged optics, and the latest advancements in optical I/O. There's a lot of fascinating research happening in those areas. And it's not just about the hardware either. The development of software and tools that can fully leverage the power of these new optical interconnects will also be crucial.
It's a multidisciplinary challenge, just like AI itself.
It is. And the progress we make in these areas will have a huge impact on the future of AI. It will determine what's possible, how accessible it is, and ultimately how we use this incredibly powerful technology to shape our world.
Well said. It's been a fascinating deep dive into the world of AI hardware and interconnects. Thanks for joining us on this journey.
My pleasure. It's always a treat to explore these cutting-edge topics, and for our listeners, keep those brains buzzing. Think about what those future AI applications might be. What could we achieve if data could move at the speed of thought? That's something to ponder, isn't it?
Absolutely. It's a future worth getting excited about. Thanks for listening, everyone, and we'll catch you next time on The Deep Dive.